Welcome back to this course on polymer chemistry, and in this lecture we will continue our discussion on polymer solutions, the remaining part, and then start a new topic on chain dimension, polymer chain dimensions, and we plan to just complete the discussion we were having on phase separation behavior of polymer solutions, and then in chain dimensions we will talk about size and shape on polymer chains and take different chains, freely rotating chains, chains with bond angle and short range restrictions, and then finally with long range steric interaction and excluded volume. Now, let us just complete the discussion we were having in last lecture. From Flory-Huggins equation we have seen this is the Flory-Huggins expression, and then we converted to Gibbs energy of mixing per segment in the last lecture, and which was turned out to be this. And then we said that if we plot this expression, we will find this type of general curve. These are corresponding to different temperature, and we discussed that there could be one type where the polymer is soluble in the solvent at any composition, and then there could be another type where you have in the left hand side and in this side you have complete solubility, and you have a region where you have metastability, thermodynamically unstable, but metastable for small fluctuation in composition, and then you have a completely insoluble region, okay, or unstable region. Now, these are the points, two minima who have the which have the common tangent. They are called binaural points or binaural composition, and the inflection point, which is the boundary between metastable and unstable region, they are called spinodal points. Okay. These are called binaural and these are called spinodal points. And now, you can see that these both the binaural points as well as the spinodal points, they are actually temperature dependent. If you change the temperature of your polymer solvent mixture, they will change. So, these are the possible different temperature where T6 is the highest and T2 greater than T1 and so on. Now, what we are going to do? We are going to plot these binaural and spinodal points with respect to temperature. So, if you have T, then at T1, say this T1, you have two binaural points and two spinoidal points. Okay. At T2, you have again this is the binaural points and these two are the spinoidal points. So, you have binaural points here and you have spinoidal points here. Like that you plot T3 and T4 and T5, T6 and so on. So, finally, you will get, so this you get these points. Now, you join them, you join to get a line for the binaural points and a line for the spinodal points. So, if I want to join them at different temperature, I will get a line for the binaural points, this is for binaural, and then similarly I get a line for the spinodal points, which will coincidence or converge in the same temperature, which we call Tc, critical temperature, and the corresponding composition here is phi 2 C, which we discussed in last lecture here. So, you get this is basically a plot of polymer phases with temperature changing and with different composition. So, if I this is the region where this is unstable or two phase system, this is a metastable system which is thermodynamically unstable, but metastable, and this outside is completely stable. Now, if you start if you start from here, a point from here, a composition corresponding to this corresponding. So, if you start a point here, obviously this is a single phase system soluble, and then if you cool the temperature, what will happen at this temperature? They will start precipitating. So, they will start forming two phase system, because this is, though it is metastable, but it is thermodynamically unstable. Similarly, if you start from this temperature, this point, this composition, then they will start precipitating this temperature. Okay. So, if you change the composition, obviously the temperature at which the two phase or the precipitation starts will vary. Okay. These points where this two phase actually generates, or the polymer become insoluble, they are called cloud points. Okay. Whereas, for this composition, at critical temperature it will start forming two phase, or the polymer become insoluble. Above this temperature, you have for any composition they are insoluble. Okay. So, basically this temperature is called upper critical solution temperature, and that happens because if you remember our excess chemical potential term, now it can be expressed, we have expressed earlier in two component, it contains two component, one is enthalpic excess molar enthalpy and one excess molar entropy. Now, both these excess term also dependent on the temperature as well, and you can also express in terms of polymer solvent interaction parameter, and finally with entropic parameter. Now, chi, which is a polymer solvent interaction parameter, also temperature dependent. Now, most cases, most of the polymers, this entropic term is negative. Most of the, in case of most of the polymers, as we have seen earlier, this entropic term is positive. Okay. So, at some temperature which is higher than theta temperature, this excess term will become positive and you will start getting precipitation. Okay. So, these are the corresponding temperature, and you in those systems you will get upper critical solution temperature. Now, in some polymer system which are not very frequently observed, you get this type of behavior which is in lower critical solution temperature, where the entropic term is negative. Okay. For one example, very common polymer nowadays used in research is poly N isopropyl acrylamide. Now, this polymer poly N isopropyl acrylamide, this has a hydrophobic group. Okay. Now, if you dissolve this polymer in water, what happens? These two groups participate in hydrogen bonding with water, but because this hydrophobic group, to hide these hydrophobic groups from water, the water molecules form structured around this hydrophobic group, which we call hydrophobic hydration or cage formation, and results you get a negative entropy. The entropy actually comes down because of structuring of the water molecules around these hydrophobic groups. Okay. Now, in addition to the combinatorial entropy, which is always favorable in mixing process. In this case, this entropy, because of contact between the polymer and solvent, which is opposing the mixing process. So, in this case entropic parameter is negative. So, psi is negative. So, what happened then, unless you have the temperature lower than theta, you will not get the solution. So, what happens, as you go down in temperature, you get from insoluble system to soluble system, and when that the particular temperature, when that happens for all composition, we call that temperature at LCST. Now, LCST can be observed for these two cases as well, where you have psi parameter negative. Another example is polyethylene glycol. You can also have LCST because you have a strong interaction between the polymer and the solvent. Now, what we have seen in last lecture, that if you this spinodal binodal points for these binodal points, this you have first derivative 0, for spinoidal points you have second derivative 0, and for the critical points where both spinoidal curve and the binodal curve merges, the third derivative is also 0, and if you just use that formula for gives free energy, this formula, and differentiate with phi 2, then you will get these expressions. Now, if you know the dependence of chi with temperature, then you can find out the spinoidal points, and the critical points is given by this expression, and if you can combine these two, you can get the critical entropy polymer solvent interaction parameter by this expression. So, let me write it again. So, critical composition at which the polymer starts separating out from solution is given by 1 by 1 plus x half. X is the number of segments, chain segments, which is always very high. X is always much greater than 1. So, you can write 1 by x half. So, the critical concentration at which the phase separation first appears from going from a two phase region, from one phase region to two phase region, is thus predicted to occur at very low polymer concentration. If we have say polymer having molecular weight of 1 million 10 to the power 6 gram per mole, and then if you have the repeating unit molecular weight which is 100, this is the repeating unit molecular weight, then x would be close to 10 to the power 4, it could be close to 10 to the power 4, then phi 2 c would be 0.01. So, basically if you have very high molecular weight, then the concentration at which the polymer start from going from becoming from one phase system to two phase system is very low. Okay, if your polymer molecular weight comes down, then this goes to little higher concentration. Now, you also know, so again this shows that the critical composition at which the polymer becomes one phase system to two phase system is highly dependent on the molecular weight, because this is also proportional to molecular weight. So, you can write molecular weight to the power half. So, as the molecular weight increases, this goes to lower and lower composition. Now, you can, so this we can also write from our previous knowledge that this is the enthalpic parameter, this is entropic parameter, and theta is kappa T psi. So, we can write minus psi 1 by theta by T half minus chi. We can set T is equal to T c and theta is equal to theta c. At T is equal to T c, chi is equal to chi c, we can write from this minus psi 1 minus theta T c to half minus chi c. Chi c we have already got from last expression. So, that is half minus half that is just 1 minute. This is chi minus half. Let me do it again because some confusion, just do it again. So, kappa minus psi we know sub theta is T by psi. So, minus these are the expressions we know, and from there we can write 1 by T c for large x, we can write 1 by T c is 1 by theta 1 plus b half, where b is v1 v1 So, if this V bar is specific volume of polymer and V1 is molar volume of solvent, then we can write the number of segments like this, and we define the term B as this. So, we can for large x we can remove or discard this, ignore this term. So, we can write this. Okay. So, which means that 1 by T c is proportional to 1 by m to the power half. That means, the critical temperature is again like the critical composition. In this case, critical temperature also varies with the molecular weight. So, if your molecular weight goes up, then your critical temperature also will go down. We have seen earlier that if your molecular weight goes up, critical composition also goes down, and in this case we are seeing that if molecular weight goes up, then critical temperature also comes down. So, we can plot these two. We can see what we have observed. This is experimental curve for observed for solutions having polymer and solvent having upper critical solution temperature. So, as the temperature goes up, this is temperature. As the temperature goes up, the critical temperature also goes down, and the critical composition at which the phase separation take place, they also becomes lower. Okay. This is experiment curve which we just seen from theoretical calculation, that if the temperature goes up, both T c goes up and the phi 2 comes down. Now, this expression is also throws up one more interesting conclusion, that if say molecular weight is very high, close to infinity, then 1 by T c would be equals to theta, or theta would be equals to T c. Okay. If m is goes to infinity or m tends to infinity, then T c is equals to theta, which means that critical miscibility temperature theta is your critical miscibility temperature in the limit of infinite molecular weight. Okay, so, that is another observation we can make from this expression. Okay, so, now we completed our discussion on the polymer solutions and then phase separation. Now, what we now will go, we will shift to the another topic, which is chain dimensions. Now, what do we mean by chain dimension? What will happen in typically, how do you write polymer? When you have seen in the books or in I have seen me always writing polymers like this, okay, something like this. We never write polymers like this. Okay. And do we write? We never write polymers like this. We always write, whenever we represent in polymer, we write a coil chain. Okay. Now, that is because because the polymers are long chain, and you have there is a numerous possible conformations, because you have a rotational freedom across the backbone, and if the polymer chain rotates across the backbone, obviously you will get different chains, different conformations, and the backbones are quite flexible in case of polymer. So, that the reason you get this type of conformation most of the times. This is let us consider a simple polyethylene molecule. This is the chemical expression. Now, this does not capture the numerous conformations a polymer chain exists. Now, as we said that existence of these numerous conformations results from the rotational degree of freedom that a single bond allows. You can, depending upon the substitution, the rotation across a single bond always allowed. Okay, now, if you have so many bonds in case of so many single bonds in case of polymer. So, polyethylene you have so many single bonds. Now, each one you can rotate, they are rotatable. So, that is the result, you get so many conformations. Now, as you have these so many conformations, the size and shape of a polymer molecule will depends on obviously chain length, and as the chain length goes up, you expected the polymer size will also go up. Obviously, secondly, it depends upon the chemical structure or chain stiffness. Now, if you have a say polyethylene molecule or say a polystyrene molecule, obviously, the rotational freedom across the single bond will be much lower in case of polyethylene than polystyrene. Because of the bulky substituent, the rotation across the single bond will be restricted in case of. So, polystyrene is a stiffer chain. We will say that it is more stiffer chain than polyethylene, or in other words, polyethylene is a more flexible chain than polystyrene. Okay. But still, in spite of being this phenyl side group, it is also having significant freedom across the single bond, rotational freedom across the single bond. So, it will also be on coil shaped, but the degree of coiling may be lower than more flexible chain like polyethylene. So, if the third one is of course, the molecular environment, which depends upon where the polymer is. If the polymer is in a solvent, then obviously, if the interaction between polymer and solvent is higher than or mean interaction between solvent and polymer, then the polymer solvent interaction will be preferred. So, the polymer will try to expand its chain, so bigger in size, and if the polymer solvent interaction is lower compared to the mean interaction of polymer and solvent, then it will try to contract and avoid the solvent molecules. Now, if the polymer is present in a concentrated solution, then one polymer molecule will come close to another polymer molecules. So, that will in effect not allow polymer to expand. Okay. So, they will again try to contract. So, these are the factors where the polymer is, it is in a dilute solution and a concentrated solution, is a good solvent or a poor solvent or a theta solvent, that will dictate the size and shape of the molecules, polymer molecule. Now, let us talk about shape first. We are using the terms size and shape. What do we mean by shape? As we mentioned that most cases we write polymer chains like this or something like this, never we write this, okay, because polymer chains, as we seen, they are having single bond where rotation across single bonds are possible. So, you get a flexible chain, and in most cases we get highly coiled, these are called coil structure. Okay, so, we get highly coiled chains. Now, if the stiffness goes up, if you make more stiff, obviously coiling, the flexibility comes down, coiling will not be possible. So, if this is like a coil structure, if the stiffness goes up, it will be like something like a worm like, okay, because it is not so flexible to become a coil, and if the chain becomes even more stiff, then finally it will be like a rod. Okay. So, this is stiffness goes up, stiffness of the backbone goes up. Most polymers we will deal in this class and we come across in application, they are falling in this category where the polymer is enough flexible to be close to a random coil than a worm like or than a rod like. So, the conformation of the flexible chain looks like random flights of diffusion of particles. When particle, say gas particle diffuse, what happens? Gas particle moves here, here, here randomly, okay, random flight, we call this as random flight. Now, polymer segments or polymer bonds cannot be so random, because you have restriction of this length. Each gas molecules can move like this, it can take any steps wherever it wants and any direction, but in case of polymer molecule, steps are fixed as the bond length of the each the bond length of the backbone repeating unit, and there are restriction of fixed bond angle, and there are restriction of also on the rotational. We will come and talk about those in details. What I am telling, it's in case of polymer also it takes the segments takes random flight, random walk, but not as freely as a like the gas molecules do in case of diffusion. Because it takes random walk or random flight, we call this the conformations of flexible polymer in solution or in melt as random coils or a Gaussian coil. Okay. Now, let us talk about size. We have talked about shape, it could be random coil, it could be worm like, it could be rod like, and most cases in polymers we deal with they are enough flexible to become closer to a random coil. So, we will discuss only about the random coil, not about the other two conformations of polymer molecules. Now, let us talk about size. What is size? When you write a polymer chain like this, as we saying all the time that we write polymer chains like this. Okay. Now, what do we mean by size? Of course, one of the basic size is contour length. Contour length is basically n multiplied by L. N is the number of bonds and N is the number of bonds and L is the length of each bond. So, basically if you arrange all the bonds one after one, all the bonds, the length will give you the contour length. Now, which is impractical in a polymer chain or any chemical chain will not have this type of arrangement. So, this is just a theoretical number. So, that is the maximum theoretically possible length one polymer can have if you can just put all the bonds in straight line one after one. Now, we said this a polymers behave like this, okay, in random coil. So, another dimension we can have is like end to end distance. So, if this is one end and this is the another end where we have R, we call end to end distance. Now, is this polymer conformation is fixed? No, it is not fixed, because there are continuous rotational across the single bond. So, you may have one now and immediately after next moment you may have this where the ends are this apart, or next moment you can have something like this where the ends are like this. So, as the polymer conformation is changing all the time, you cannot have a fixed value of end to end distance, because this might have some value which is different from this value, which is different from this value. Okay. So, what we do is statistically we find the probability of finding one length how much, and then use this term where this represent time average. Okay. So, you with time what is the average? R square to the power half. So, that is the root mean square end to end distance. So, this because the polymer change is always changing its conformation, you cannot write a fixed R, you have to write a statistical parameter which is given by a root mean square end to end distance. Now, the third parameter which we can mention is like a radius of gyration. Its radius of gyration is defined as the root mean square distance of the elements of chain from center of gravity of the coil. So, if you have a coil and if this is the center of gravity, then all the segments. So, these are the distance of all the segments, okay, all the elements, numerous numbers. So, 1, 2, 3, 4, 5, 6, 7, 8. So, root, if this is 1 is S, again the root mean square distance of the elements of the chain from the center of gravity or center of mass of the coil is called the radius of gyration. Now, fortunately there is a this two term root mean square end to end distance and root mean square or radius of gyration are mathematically related. So, if you find one, the other would be, you can get easily from that expression which both connects each other. Now, out of these two, this this radius of gyration is similar to, is almost like the radius. If you consider the polymer coil as a sphere, if you consider this coil as a sphere, then this radius of gyration is similar to or proportional to the radius of this sphere. Okay. So, the solution properties of the polymer chain and say light scattering behavior as well is mostly dictated by the radius of gyration value, and is also useful if you have more than one ends, like if you have branched polymer, then you have more than two ends, then end to end distance is not existing, which one to take. So, in that case, or if you have a cyclic polymer where there is no ends, then end to end distance is also not possible. So, in those cases it is useful to use the radius of gyration is more useful, whereas in the root mean square end to end distance is more useful for describing the rubber elasticity behavior of a polymer coil. Okay. So, the radius of gyration gives more, or gives the solution behavior of a polymer coil is mostly dependent on the radius of gyration, where the rubber elasticity is governed by the root mean square end to end distance. Okay, now let us find out the size of a simplest molecular model. Now, what we will first consider, we now want to find out these values or these values. Now, if we can find one of them, we know that both these are related mathematically. So, you can find easily the other one. Now, we will mainly calculate or find information about this, and we will know the expression for with this, and then find out what is the relation, how to get this. Now, let us first consider the simplistic, very simple model where you have freely jointed chain with no restriction. So, if you have bonds, you have no restriction. So, if you consider this as a one bond, then the other bond you can place anywhere without having any restriction of bond angle or the rotational restriction between them. So, this is given by this. For this, the model is developed, and that is again which you just mentioned, this the expression for this chain is given by random walk model, which was first developed for the movement of ideal gas. But here the difference is that in case of ideal gas, the steps the gas molecules can take is it does not matter, it can take any value, but in this case the each step the polymer can take or the bond can take is the length of the bond. So, you can start from one point, one end, and just put the other randomly. Of course, the chain length, the length of the each bond has to be equal. So, you can place I am placing this randomly. Okay. So, you start from one end and you continually adding the further bonds in a 3D space. We are just showing a 2D picture here, but you imagine this is in 3 dimensional. Okay. So, this is how the random walk model is designed. So, what is I can continue in a random way. So, one end is here. So, what the model do, make a 3 dimensional coordinate where the one end is placed as the origin of this coordinate, and this is r. From the what is found is what is the probability of the other end be at a distance of r from the origin. The way this model works is that you do put the one chain in at the origin of a 3D coordinate and found out what is the probability that the other chain end would be a distance of r from the origin. So, if you put this is x, y, z, then the probability of that the other end would be a point x, y, z, which is having a distance r from the origin, would be given by where this is probability distribution density function. which is the probability per unit volume. So, if you are considering one volume, unit volume at a distance r, and you are trying to find out what is the probability of that volume have the other end. When n is large, of course, r is the end to end distance is much lower than NL, then we have this equals to we have this, the expression for this, we have this where beta is now. Here we are considering one unit volume in this place. Now, there could be other points which are also having the same distance r. We can have other values r across these 3 coordinate. So, you cannot only consider unit volume, you have to consider the volume element at distance r from. So, you are not considering one point, you are considering the entire volume element which is having distance r from the origin, where you find the probability of finding the other chain end, and that can be written as so we are adding a volume element here with a radius of r. Okay. 4 pi r square dr is the volume element. So, we are finding the probability of, this is the probability distribution function. So, total probability of finding the chain other chain end at a distance r would be the probability distribution function multiplied by the volume element. Okay. And this one is WR is then given by this is radial distribution function, and the other case it was Gaussian distribution function. Now, by this you may not have to remember all this approach unless you are extremely interested to know the logic behind to get the final expression. But what I am trying to understand how the approach, what is the theoretical approach is made to find out the end to end distance, root mean square end to end distance for a random coil, and this is how it is made. And finally, if we neglect or ignore all the steps, we can that is not required or we cannot have enough time to complete that. What we can write, that it will finally give the end to end distance like this. Okay. So, if you From these expressions you finally get a expression, and you remember this, and you do not have to remember all the steps unless you are required, unless you are interested very much. Now, this subscript f we are mentioning as for freely rotating chain or freely jointed chain. Freely jointed chain, that means he does not, freely jointed chain does not have any restriction of bond angle and bond rotation. As I said that fortunately there is a relation for large n and for linear molecule we can write this is your radius of gyration. So, these relations can be shown that, so if you know this, so if you put f here, if you put f here, so freely rotating chain we can get this expression. So, we are writing for a simple model, molecular model which is freely jointed chain with no restriction, we now shown that using Gaussian distribution function or random coil approach, it can be shown that it shows this, it has this relation, which means that coil dimensions will be significantly lesser than the contour lengths. If you have a molecule of say 10,000 units, 10,000 repeating units. If you have say polyethylene molecule, just compare polyethylene molecule with 10,000 repeating units, each carbon length is 1.54 Armstrong. So, the contour length would be, to multiply this by the number of bonds. So, it will be less than 1 in true sense, but we are ignoring that. So, it will be contour length, whereas your RMS end to end distance would be 154 Armstrong, which is 100 times lower than the contour length, and that is coming from this n to the power half term. So, because there are 10,000 units, n is 10,000, you are getting 100 times lower value of the contour of the RMS end to end distance. As we seen that it can be shown that the radius of gyration can be found from the RMS root mean square RMS end to end distance, and as I said earlier, the RMS end to end distance is useful for rubber elasticity, and the radius of gyration useful for dielucidation properties and light scattering, and it can also useful for branch molecules and cyclic molecules. Now, that is not practical, a chain without any restriction, bond angle restriction or bond rotational restriction is physically unrealistic. So, any real polymer chain will have restriction of bond angle and also restriction for the single rotation around the single bond. So, there are actually three interaction: bond angle restriction and short range restrictions which is coming from the single bond rotational restriction, and there is also long range steric interaction and excluded volume effect, which we will encounter one by one and see how the dimension or the size of the polymer changes. This should be size, not shape. So, all this we will put in all these restriction one after one and found then how the RMS end to end distance varies. Now, once we know RMS end to end distance, we can always find the radius of gyration. Now, let us first consider these two, bond angle restriction and short range rotational restriction. Now, let us consider first a single bond, a simple bond, one bond. If you have one bond like this, now the other one, in case of freely rotating chain, you can place it here, you can place it here, or even you can place it here. Okay. There is no restriction of bond angle, or you can do it in the 3D. I am just showing in a 2D matrix. So, you can place the other bond here at 180 degree or 90 degree or even 0 degree, because there was no restriction of bond angle in this case, and as I said, I am just showing a 2 dimension. You have to imagine in case of 3 dimension as well. So, what would have been the average if all these 0 to 180 degrees is equally probable, then what would be the time average? Time would have been 90 degree. So, this should have been the time average value. So, what would have been the end to end distance? Would be from this end to this end. This would have been the end to end distance. Now, actually, say in case of carbon carbon bond, what is the bond angle? This is the time average if there was no restriction of bond angle. In case of actual, you have a not 90 degree, the bond angle is 109.5 degree tetrahedral bond angle, then your actual molecule bond angle would be look like this. So, the end to end distance which were earlier this, now it will become this. So, because of this restriction, you can now understand that the end to end distance or time average end to end distance, root mean square end to end distance will increase from here to here. Okay. So, for this restriction, you will have increase in the root mean square end to end distance. Now, it can clearly shown this value where we are writing FA, which is angle restriction from bond angle is coming. We are writing this, it can be shown that 1 minus cos theta 1 plus okay. Now, as most cases carbon carbon bond or other bonds, theta is between 90 degree and 180 degree. So, cos theta is less than 0. So, obviously, r square f a would be greater than r square freely rotating. That we have just seen from the freely rotating bond. So, this is the expression which now we got from the free angle restriction. So, what we will do in the next lecture, we will impose the second restriction and see how this dimension changes.